Hello everyone. In this video I'll be reviewing through the middle section of last year's AMC10A. If you haven't yet seen the video for the first 10 problems and you would like to find out how I did the first 10 problems, you may refer to the video which I just uploaded a few days ago. I've stopped at a rather odd sounding location, which is question 19. And that's because if we actually look at the cutoffs, which are still on the thumbnail, if you solved up to question 19, you would get all the way to the highest award for this paper, which is the Distinguished Honor Roll for the top 1%. If you did 19 questions perfectly and left all the other 6 blank, you would have gotten yourself 1, 2, 3 marks, which would give you the maximum. At the same time, if you were aiming for any of the other cutoffs for AIME qualification or distinction, you would have needed to do some of this middle section. So one could say that the middle section of the AMC is the most important section because the first 10 questions, it's sort of expectation. The last 5 or 6 questions are sort of like a bonus, but the middle section is where you will hit all of these various thresholds. So without further ado, we're going to go through the questions in this all-important middle section. So to put a number to it, right, if you had done, let's say, 10 problems with 15 blanks, you would currently be at 82.5 marks. And each additional correct answer gives you another 4.5 marks. So if let's say you were hoping to get any of these targets, you would need at least 13 or 14 questions. So you would hope to be able to solve at least some of these. If you are aiming to get the Distinction Honor Roll, Distinction or a Distinguished Honor Roll, you would want to also solve some of this a bit more quickly. But if you're just hoping for AIME qualification, it's important more to be able to solve this than to solve it quickly. Now, question 11 is an example of this. So Ted mistakenly wrote 2 to the m times square root 1 over 4096 as 2 times the mth root of 1 over 4096. What is the sum of all real numbers m for which these two expressions have the same value? Now the one thing about AMC is that it helps to know your numbers well. So what I know is that 4096 is 64 squared. I also know that it's a power of 2 and it is 2 to the power of 12. So that would allow me to do a very quick conversion. 2 to the m times 1 over 64 is going to be equal to 2 times 2 to the power of negative 12 over m. 1 over 64 is 2 to the negative 6. So really I have 2 to the m minus 6 equals 2 to the 1 minus 12 over m, which means that I can just equate these two and get a quadratic after I multiply through by m. So factorize m minus 3, m minus 4 equals to 0. Put back the m equals to 3 and 4. We see that nothing's going to go wrong. There's no negative numbers, so I don't have to worry that things will get messed up. The answer is just 3 plus 4 equals to 7. Question 12. This is a long logic puzzle question. On Halloween, 31 children walked into the principal's office asking for candy. They can be classified into 3 types. Some always lie, some always tell the truth, and some alternately lie and tell the truth. So, always lie, always tell the truth, and alternately lie and tell the truth. The alternators arbitrarily choose the first response, so we don't know where they start from. Now, the principal asked everyone the same 3 questions in this order. So, order matters because of the alternators. So, are you a truth teller? The principal gave a piece of candy to each of the 22 children who answered yes. Are you an alternator? The principal gave a piece of candy to each of the 15 children who answered yes. And are you a liar? The principal gave a piece of candy to each of the 9 children who answered yes. Now we can think about it and say, when will a person answer each of these? Now the truth tellers is the most straightforward. The truth tellers will only say yes to the first question. Now the liars will say yes to the first 2 questions. Now the alternators, it depends. But if we look at the bottom, the answer is there are 9 children. So there are the alternators who start with telling the truth, and there are the alternators who start by lying. Now, if the alternator is telling the truth, they will not say they are a liar. So the alternators who started with a lying would have appeared here, and then they would also have appeared here, because in the second question they are telling the truth. The alternators who start by telling the truth don't appear in the first question, then they lie, so they don't appear in the second question, then they tell the truth, so they don't appear in the third question. So in other words, this is all the same group. Now that means simply that I can read the 9 is here, 15 minus 9 is 6, and 22 minus 15 is 7, would be for these 3 groups. And the children who always tell the truth are here, so your answer is 7. Now some of you are really good at these kinds of questions. If you personally tend to always read the question wrongly, or it just frightens you, this is the sort of question which I could suggest you skip it first and come back to it if you have time. Because it may take an unduly long time for some of you to work out, which is not worth it. Even though this is not a super hard question, it can burn up a lot of time if you get confused. Question 13. Now when I see a question like this with no diagram, just very quickly draw a rough diagram. So don't need to be too perfect, and then we'll adjust later. So ABC is a scalene triangle. P is on BC such that AP bisects BC. The line through B perpendicular to AP intersects the line through A parallel to BC at point D. Suppose that BP equals to 2, PC equals to 3, what is D? What is AD? Now, I'm a bit fortunate here. I expected this to be quite bad because I just drew this question at random, and then I realized that, okay, the 2:3 looks serviceable. But that only took about 15 seconds. So if your end result is, whoops, BP is 2 and BC is 3 looks very wrong, then just draw a second diagram. At least you know where everything goes right now. Okay, so what do I do with this? Now, the first thing is that I'll just grab all the obvious information. Now, the first obvious information comes from my angle bisector theorem. Now, the angle bisector theorem would tell me that AB to AC is 2:3 because of the 2 and 3. Now, at the same time, by symmetry, I can see that these two, I should probably call this name, these points, let's just call it X and Y. I can see that AB and AX are equal because ABY and AXY are just reflections of each other. So because of that, it means that if this is 2:3, I can write this as 2x. I should not use x, I shall just call this 2m, and this is 2:3, so this is m. I always talk about this hourglass pattern, and this hourglass pattern here will give you a pair of similar triangles because of equal angles from the parallel lines. And so this is enough for us to find AD, because AD to BC would be equal to AX to XC, which is 2. And so AD is 2 times 5 equals to 10. Question 14. What is the number of ways the numbers from 1 to 14 can be split into 7 pairs such that for each pair, the greater number is at least 2 times the smaller number? Now for this one, greater number is at least 2 times of the smaller number. Let's just write down all the numbers and then think about it in terms of what kind of choices do I actually have. Now the first thing that you realize is that none of these can be the smaller number. And so therefore, the pairs actually are going to be one of the bottom numbers paired with one of the top numbers. And the ones below are the greater number, the ones on top are the smaller numbers. So this will be the big number, this will be the small number row. Now, if I were to look at this, I say that 7 needs 14. That's the only one that is at least 2 times of that. So, in a way, that doesn't affect my counting, because I want to know how many ways there are, so that is fixed. Now, at the same time, 1, 2, 3, and 4 can do whatever they like. So 6 has 2 choices, and 5 has 4 choices. But of course, I should choose the one for 6 first, and then that means I have 2 choices, one of which is going to be removed from the choices for 5. So 5 will have 3 choices. And then the others can be paired to anything. So it's just going to be 4 factorial, 4 times 3 times 2 times 1. So 2 times 3 times 4 factorial is going to be equal to 144, which is option E. Now at this point, if you had gotten your first 14 problems correct, and if all the other 11 are blank, you would get 100.5. Now, as you have seen a moment ago in the thumbnail, the distinction mark is 100.5. So if you had just gotten to here in 75 minutes, you would get a distinction. But again, caveat, you don't know the cutoff score beforehand. It changes with every paper. Nonetheless, I think this is actually very attainable time-wise, because between the last video and this one, and a lot of my sidetracking about AMC formats and scoring, we have taken a lot less time than 75 minutes. So very achievable time-wise. The main thing is looking for questions that you can do. Now, as we move through these sections, you realize that the difficulty is a bit subjective. For example, quadrilateral ABCD with side lengths AB equals to 7, BC equals to 24, CD equals to 20, DA equals to 15 is inscribed in a circle. Now, it's a little bit difficult to solve this without just observing a very simple fact, which is that 7, 24 and 20 and 15 both contribute to the same Pythagorean triple. In other words, we can just take it as it's 7, 24, 25, and another side of it is a 20, 15, 25. Two right-angled triangles. Now, of course, this is a little bit of what we often call hand-waving, because how do you know this is the only possible way? And I guess the answer would be that it is not the only possible way, but because I need it to be a cyclic quadrilateral, this makes sense. And I trust that if there's another way of doing it, such that it's also cyclic, it should also give me the same answer. So just take the convenient assumption and very quickly move on. So if you notice this, the question is very easy because area interior to the circle but exterior to the quadrilateral. Interior to the circle has diameter 25. So it's just going to be pi times 25 over 2 squared. Area of the quadrilateral made up of two triangles, half times 7 times 24, half times 15 times 20. And so after a very quick calculation, A plus B plus C, once I write it in this format, is 1565. Question 16. The roots of the polynomial 10x cubed minus 39x squared plus 29x minus 6 are the height, length and width of a rectangular box, which is a right rectangular prism. Forgot to close the bracket. A new rectangular box is formed by lengthening each edge of the original box by 2 units. What is the volume of the new box? You could try to factorize this, but the difficulty with trying to factorize a cubic is that it's hard to tell when is it that I have failed to factorize because I didn't notice the root, and when is it doesn't have any nice roots. So it's better to err on the side of not factorizing unless it is very obviously some sort of a cubic identity like a sum or difference of cubes. So instead, we can use our Vieta's formulas. Now, I'll just call the length, height and width, I'll just call them P, Q, R. It's easier than using H, L and W. Vieta's formulas would tell me P plus Q plus R is 39 over 10. PQ plus QR plus RP is 29 over 10. And PQR is 6 over 10. Or 3/5. I'll just leave it like that for now. Now, based on this, a new rectangular box is formed by lengthening each edge by 2 units, means that you have to calculate this, which would be quite okay. If you expanded it out, you get just the same stuff that come out from Vieta's. So this would have given you 30. But, and this is very important, there is a much faster way to do this as well. If you understood where Vieta's comes from, it actually comes from just writing down a factorization like this. And saying that if I expanded it out and compare coefficients, this would give me Vieta's. Now, why would it be better here? It would be better because if I wanted to find this expression here, I can just sub in x equals to minus 2. Now, letting x equals to minus 2 would immediately make this expression into what you want, just the negative of it. And of course, divide off by 10 later. So a substitution later. Minus 80 minus 152. 156. Minus 58 minus 6 would give you negative 300. And so your answer is indeed 30 as well. So this would be a lot faster if you had noticed it. Of course, if you didn't notice it, then the Vieta's method would also work. Both of these give you the same answer, which is 30. Question 17. How many 3-digit positive integers ABC are there whose non-zero digits, so take note, non-zero digits ABC satisfy 0 point ABC is 1/3 0 point A repeated plus 0 point B repeated plus 0 point C repeated, and all of these are repeating, so ABC repeated like this. Now I can immediately convert all of these into fractions. So ABC repeating is just ABC over 999. A, B, and C separately repeating is just A over 9, B over 9, and C over 9. Of course, ABC is not A times B times C, it's still the 3-digit number ABC. Multiply throughout by 999, you are going to end up with the 3-digit number ABC is 37 times of A plus B plus C. Now, what do I do with this? Well, it is possible to just start listing. It is also a bit annoying to start listing because you are going to have a lot of cases to work on, since all the options suggest quite a lot of cases. So I'm going to just convert this into 100A plus 10B plus C, and then just group them. 63A equals 27B plus 36C, and I can divide by 9. 7A equals to 3B plus 4C. Now it's pretty clear that A equals to B equals to C will work. So that already gives you 9 possibilities, right? That's the 9, that is the smallest option. Although I suspect there should be some others. Now, in order for them to be some others, the way that it goes is that if I've got, let's say, 3B plus 4C, which is a multiple of 3 and a multiple of 4, I can replace 3 4s with 4 3s. So whenever A is big enough, I have this possibility of switching between this stuff. So for instance, if let's say A equals to 4, right? So I'm saying that it's 3 times 4 plus 4 times 4. I could theoretically replace 3 of the 4s with 4 3s. So 7 times 4 is equal to this. I can replace 3 4s with 4 3s, which essentially gives me the next number, 481. I can't go the other way because if I went, you get 3 times 0, so I can't do that. Now, this is the plan that I have for all of these. If A equals to 5, then 7 times 5 is normally 3 times 5 plus 4 times 5, but I can replace it by 4 more 3s like this, or I can replace 4 3s by 3 4s. So actually in this case I get 2 more numbers. If A equals to 6, now I can't get 4 more 3s because that gives me a digit which is 10, and 10 is not a digit. So I can only replace away the 4 3s with 3 4s, and this gives me another combination. And basically that will be it, because for anything beyond the 7 times 6. So if I put A equals to 7, 8, or 9, there is no way that I can replace and add 3 more without overflowing the limit. So these are the 4 bonus ones, in addition to the standard digit repeating cases. And so therefore I should get 13 in total, which is option D. Question 18. Let Tk be the transformation of the coordinate plane that first rotates the plane k degrees counterclockwise around the origin and then reflects the plane across the y-axis. Okay, so it means that, let's say I'm here. First I rotate by k degrees, and then I reflect it over the y-axis, and so the end result is you came from here to there. What's the least positive integer n such that performing the sequence of transformations t1, t2 until tn returns the point 1, 0 back to itself? Okay, so this is interesting. It's interesting because all I'm doing is a lot of reflections and rotations. So even though it says the plane, I know that all I'm going to be doing is just to do a bit of rotations and reflections, and for the initial stage I'm just going to keep on flip-flopping over the y-axis between the first and second quadrant. So what I'm going to do is I'm going to just note down where it is in the unit circle sense of things, right, where this is 0 degrees, 90 degrees, 180 degrees, and 270 degrees. I'm just going to note where I am at in an angular sense. So I start with 0 degrees. Now T1 gets me to 1 degree and then reflects it to 179. Now T2 gets me to 181 degrees and then reflects it to 359. Now T3 gets me to 2 degrees and it reflects to 178. T4 gets me to 182 degrees and then reflects me to 358. And this actually is quite an obvious pattern, right? I mean, it will just continue on, and one could go about and prove it a bit more rigorously, but I think it is obvious enough that one is quite assured we can just continue on. Now I want to know when it first goes back to 0 degrees. So after T1 you are at 179 degrees, after T3 you are at 178 degrees, after T5 you are at 177 degrees. So if this pattern continues, it should mean that every 2 transformations reduces it by 1 degree. So if I just use the first one as a reference, after this 179 times 2, I get 359 as my answer. And so that is option A. Now you do have to take this kind of a risk sometimes, meaning that is there any weird exception that might take place somewhere in the middle? To be honest, you can check it, but it's worth the risk unless you are exceedingly fast. By this point you are running out of time, and so you want to make sure that you are just giving yourself the best chance of at least attempting 1 or 2 other questions, which I shall attempt 1 other question in this video, which is question 19. Define Ln as the least common multiple of all the integers from 1 to n inclusive. There is a unique integer h such that the sum of 1 over 1 plus 1 over 2 all the way to 1 over 17 is h over L17. What is the remainder when h is divided by 17? Okay, so what is the remainder when h is divided by 17? I can multiply both sides by L17. Now, needless to say, L17 is the least common multiple of 1 to 17, so it is a multiple of 17. Now, since it's a multiple of 17, if I divide it by anything other than 17, all of it, all the way up to the L17 over 16, all of these will still be a multiple of 17. So because they are all multiples of 17, I sort of can say that is irrelevant. I only need to know what is this quantity modulo 17. So what is this quantity modulo 17? Now, the easiest way to do this, because LCM is just LCM, the easiest way to do this is just to find the LCM. Now, how you find the LCM is you look at each prime number up to 17 and ask yourself, what is the biggest power from 1 to 17? Now, the biggest power would be the one that you need to satisfy, because think of it as the LCM is just satisfying a bunch of greedy numbers that says, no, give me my factors, give me my factors. So, L17, the biggest is 2 to the 4, which is 16. There's 3 squared, which is 9. And everything else is just a singleton. Throw that away. And just take this thing mod 17. So 16 is negative 1. 11 is negative 6. 13 is negative 4, and then we just kind of go down the road. So this is minus 9. I should just do them 2 at a time, right? Minus 1 and 9 is 8, 5 and 7 is 35, that's 1, okay. Minus 6 and minus 4 is 24, that's 7. Then 8 times 7 is 56, 56 gives you 5. So 5 mod 17. Option C is your answer. Okay, so this was just a very, I think, manageable selectively middle section of the AMC10. So you would not find all the questions easy, but I'm sure that many of you would find some of these questions to be quite doable. Yeah, once again, before we end off, thanks for watching, and a reminder that you can register for the AMC 10 and 12 for Singaporeans only through the link that is provided in the description below. If let's say that your school offers you the AMC 10 and 12 but does not offer you classes and you are keen to join a short-term class with me, the details are also provided. The class will run in the end of October up to the first week of November. So thanks for watching, please like and subscribe, and see you next time for the last section of this AMC 10 paper.